Hello everyone, welcome to the 29th lecture in the series. In today's lecture, we are going to explore an algorithm for finding the shortest path from a single source. The algorithm's name is Dijkstras algorithm. So, we will be learning the steps associated with Dijkstras algorithm, probably solve one or two examples on how this algorithm works on a graph data structure, and we will be solving some of the questions that could be asked from this particular topic. So, let us first explore what shortest path means. Consider that we have a weighted directed graph, and in that graph we have set of vertices and edges, and we are going to make use of every node in that graph to represent a city, and there could be edges on the graph between the nodes, and that actually mentions that there is a path from that particular city to the other city, say from city X to city Y, and there will be weights associated with that edges, and that weights actually denote the cost of travelling from city X to city Y. And the problem here is that we are supposed to find the minimum cost to travel from city X to city Y. So, in order to find a solution for this problem, we need a way that helps to find the shortest path from starting from city X to city Y. So, for solving this kind of problems on a weighted directed graph, we go for learning a particular algorithm called as Dijkstras algorithm. Hope you remember that in the very first lecture I was telling you the various algorithm or problem solving strategies, of which one of the strategies is called as a greedy approach. So, in a greedy approach, what we do is that once we get a solution for a problem, we do not stop with that. Our objective is to find the optimal or the best solution for the problem, and so we greed and try to find even more best solution for the particular problem. So, the thing to be noted here is, in a greedy approach, as soon as we get a solution, we do not stop, rather we go for some iterations and check whether there exists even more better solution for the particular problem. So, that way of looking for solutions, we call it as a greedy approach. So, here in this lecture you are going to learn about one of the algorithms that is based on this greedy approach called the Dijkstras algorithm. So, this is the formal definition for finding the shortest path for a graph. I mean, it is a single source shortest path problem. So, what single source shortest path problem is that we will have a node or a vertex designated as the starting vertex, from which we actually start our travel, and we are supposed to find the shortest path from the start city to the destination city. So, here given this problem, in order to find the shortest path, this is going to be the formal definition. We will be having a weighted directed graph, and we are going to end up with the path that starts from the start vertex X and ends at the destination vertex Y. And our aim is to find the cost for that path, and that path cost should be the least of all. And for finding the cost of that path, we may have to sum up the weights associated with every edge. Say for instance, if I have a path say A, B, C, D, which includes 4 vertices, then the path from A to B will weight of the edge between A and B, and the path A, B, C would have the weight of edges between A and B summed up with weight of edges between B and C. So, that is what we have given by this equation. We have a summation. In order to find the cost of the path, we will be summing up the weights of those edges that lie along that path. And here, as our objective is to find the shortest path, we are trying to minimize the cost of this path. So, here in this case, as an example, you have a graph with 5 vertices, and you could see that all this graph is directed, and all its you could see that the weights are all given for every edge, and here we have designated vertex V1 as the start vertex, and so here we will start at the start vertex, we reach up till V2. From V2 we have only one path, just because the edges have direction associated with it, there is no other way to go. So, we could reach vertex V4, from where we could actually have two options, 3 and 8, but as this cast is less, we have picked up this path and we have entered into V3, and finally, we end up with the destination vertex, which is V5 by picking up this path. So, here this is how we actually try to find the shortest path at every point in time. From among the set of edges that originate from a vertex, we will try to pick up the vertex that comes up with the least cast. So, as I said before, we are now talking about single source shortest path problem. As such, this we will propose a solution for this problem, assuming that always the travel starts from that specific or single source. Alternatively, we have another class of problem which we call it as all source shortest path problem. In that case, our solution would include shortest path from every pair of vertices in that graph. Whereas, in case of single source shortest path problem, there will be one designated vertex or node as the start vertex, and we will be finding or proposing the solution for reaching out to all other vertices from that start vertex. And there are so many applications of this shortest path algorithm, especially in case of when you talk of real world applications like maps, say for instance with Google Maps. We always look for shortest path to from one place to another, right. So, in such cases, the actual algorithm that is being used is the shortest path algorithm, and all the places are all treated as nodes in a graph, and we ultimately find the shortest path between the nodes in the graph. And when you consider routing in a network, and say for instance, the way the packets get routed from source to destination, it follows much the similar way as you do with the maps, right. Every path will try to, every packet will try to reach the destination system along the shortest route, and the algorithm that is being used underlying is that shortest path algorithm. And be it flight reservation system or be it a driving direction giving system, in all cases we normally you make use of this graph data structure underlying, and for finding the shortest path we make use of this single source shortest path algorithm. And there are certain properties of this shortest path. The first one is that the subpath of a shortest path is itself a shortest path. So, we actually end up with the solution as the shortest path. So, even if you consider some subpath within that solution, ultimately it should be the shortest, only then the final solution could be the best and the path with the least cast. The second property is that there is a tree of shortest path from a start vertex to all other vertices. So, given a graph, our objective is to end up with a tree, and in the tree our aim is to reach the destination vertex from the start vertex through the edges with the least cast. So, that is why we say that this is a tree instead of a graph. We give as input a graph and our expectation as output is a tree, and you know very well that in a tree you do not find any cycles and every node will be visited exactly once. So, now we move on to the algorithm that is meant for solving the single source shortest path problem. So, the algorithm's name is Dijkstras algorithm, and as I said before, this algorithm falls under the category of greedy approach to problem solving, where greedy approach means it tries to find the best solution. Even if it finds a solution, it does not stop, rather it continues with the as many iterations possible to yield the best solution. So, for this Dijkstras algorithm, it will work only if the graph is weighted and directed and without any negative weights. You should bear in mind that Dijkstras algorithm is applicable only if weights present in the edges are all non-negative. So, let us consider a graph G. and the graph is composed of set of edges where we denote every edge as a pair u comma v, and every weight along that edge is given by w of u comma v, and it is greater than 0. And now we want to find the shortest path starting from vertex v1, which is our start vertex, to any node vi. Now let us consider that we have a subset vs, which is a subset of nodes in this graph g, and we are going to find the cost of the shortest path, for which we may have to sum up the weights along the edges. So let cost of vi be the weight of the shortest path from the start vertex v1 to the set vertex vi. So in this case we are finding the cost along a path, and this path passes through the nodes in this set vs only. So as I said, Dijkstras algorithm is meant to give a solution to the single source shortest path problem. It was already used in graph theory, and now we use the same here, and this algorithm can work for both directed and undirected graphs, but all of them should have weights, and those weights should be non-negative. So this is the input to the Dijkstras algorithm. You will be giving a graph, probably we will be giving a weighted graph, and output would be the length of the shortest path from the given source vertex. That source vertex should belong to the set of vertices in that graph. This man is Dijkstra, and the algorithm has got its name from this from its inventor. So this Dijkstra is he was a Dutch computer scientist. He was the recipient of the well-known Turing Award for contribution to developing programming languages, and he is the contributor of this particular algorithm, shortest path algorithm, that is used in graph theory, and hence this algorithm got his name. And not only that, he has come up with lot many contributions like reverse Polish notation and multi-programming system, the Banker's algorithm that you learn in OS. So all of them are his contributions. So this Dijkstras algorithm is also used in routing. So when it comes to routing protocols, all the routing protocols fall under either of the two categories. One is open shortest path first, and another one is distance vector routing. And this shortest path this shortest path algorithm is being used with the routing protocol open shortest path first. So this protocol actually specifies how routers could communicate with each other, and it disseminates information to its neighbors that helps the packets to select the routes to nodes in a computer network. So this algorithm is known to be part of this widely used routing protocol, and this is how your Dijkstras algorithm actually work. The algorithm first computes for each vertex u the distance to u from the start vertex v, and that is the weight of the shortest path between the set vertices, that is v and u. And the algorithm will be keeping track of the set of vertices for which the distance has been computed, and let us for the time being call this set of vertices as cloud C, and every vertex will be having a label associated with it. We call that label as d, and for any vertex u, this label d of u will be storing the approximate of the distance between the vertices v and u. So the algorithm will keep on updating this d of u value when it makes an attempt to find a shorter path between the set two vertices. So as and when we explore a new vertex and mark it visited, the distance between the pair of vertices would try to change, and that gets updated in this particular variable d of u. And when a vertex is added to the cloud, its label d of u is equivalent to the actual final distance between the starting vertex and the time being chosen vertex, which is u. So we will see an example, then you will be probably understanding this algorithm better. Let us consider the same graph. Let us assume that v1 is our start vertex. So, here Vs is the set that marks the set of vertices that are all marked visited. We are going to construct a tree and V1 will be the first node in that tree. And as similar to the variable d of u here there in the algorithm, here we are maintaining cast, maintaining the variable named cast. So, we are maintaining the cast of every vertex. So, cost of reaching every vertex. So, we have 5 vertices in that graph and that is why we have 5 columns here. By the time we mark the start vertex as visited and we have added it to the cloud, from V1 there is only one vertex that is reachable whose cost is 5 and that is added up. And as V1 is the start vertex, there will not be any vertex entering, I mean there will not be any edge to it, and so its cost is marked as 0. And the cost of reaching all other vertices are marked as infinity, just as we do not have any other edge to any of those 3 vertices. And this is the first step in the algorithm. And next our only attempt is our only possibility is that we could enter into vertex V2, and so V2 gets added up to the cloud here. And now at this moment vertices V1 and V2 are marked as visited. Now we try to compute the distance of vertices that are all reachable from the start vertex. As you know, vertex V2 is reachable now, and vertex V4 is reachable from V2, and vertex V4 is reachable from V2. We are supposed to find the cost of reaching V4 from the start vertex, and so we sum up the cost of edges between V1 and V2 and then V2 and V4, and that is why we have value as 9 here. So, by this time we have just cost of 2 vertices that are all visited, which are 2 and 4, and their cost are shown here. And even at this moment there are no path to V3 or V4 explored till now, and so at this moment the cost of reaching those vertices are all marked as infinity. The next step is, after reaching V4, we will just look at edges that are all emanating from vertex V4. You could see that there are 2 possibilities here, and of which as the vertex between V4 and V3 is the one with the least cost or least weight, then we pick up this as the possible choice. And so, we are supposed to update the weights over here, we are going to pick it up, and so now we add vertex V4 as visited, and we have to add up, we have to find the cost of reaching the other vertex. In our case, from start vertex its cost would be 5 plus 4 plus 3. So, 9 plus 3 12. So, the cost of reaching vertex V3 is 12, that is added up here, and after that we are supposed to find the cost of reaching the other vertex from this point. So, in this case, after marking V3 as visited, the next only possibility is there is one edge emanating out of it, which is 2 V5, and so V5 could be reached from V4 at a cost of 3, and V3 could be V5 could be reached from V3 at a cost of 4. So, altogether its cost from the start vertex would be 5 plus 4 plus 3 plus 4, which is 17 here, is supposed to be the best solution. But here what you see is that by the time we mark V4 as visited, as I said, we have 2 possibilities, that is I could reach up to V3 at a cost of 3 and V5 at a cost of 8. We are updating those 2 values here. So, here you could see that the cost of reaching V3 is 12 and the cost of reaching V5 over V4 is 17. That is what we have updated at this state. In the next step, what we are supposed to do is, we are supposed to mark, choose the vertex with the least one, in our case which is V3. So, now we check whether there is any other vertex that could be reached from V3 at a minimal cost. So, there is one possibility, there is possibility of reaching out to V5 through V3, and we check the cost here. It is, as we have computed already, it is 5 plus 4 plus 3 plus 4, which is 9, 12 and 16. So, that is why the cost has been updated here. So, for all other vertices there is no change, but as you add this vertex V3 as visited, now the cost of reaching V5 has been reduced by 1, and so that weight has been updated over in this table. So, by this time we make this updation, you could see that all the vertices in that graph have been visited exactly once, and then we have got this tree as the output, and the total cost for this tree is 60. So, this is how this Dijkstras algorithm actually works. The way we solve the example, initially we have a set of nodes in the graph, we call it as n. For every node in that graph, we just fetch its weight and put it in cost of Vi, which is the weight associated with every pair of every edge. And then we initially put up only the start vertex in the set of vertices visited list, and after that for every other vertex in that graph we will try to find the smallest cost from the start vertex to itself. And if suppose it's another condition to be checked is that the particular vertex is not in the set Vs. If so, we will be adding that particular vertex Vi for which the cost is smallest, and then we will try to check with all other pairs of nodes in the set that are all not in Vs, and check whether the existing cost, that is the cost that we have computed, is greater than the cost of that vertex plus the weight of the new edge that we have just found out. If so, we will be revising that as the new cost. So, as such this loop is meant to look for a greedy solution, like whatever though we have computed the cost earlier, we just try to find whether there is yet another path that yields the least cost. So, this loop actually helps to find the least cost solution for us. So, we have one more example here where you could see that we have again a graph with 5 vertices, and initially here in this case A is our start vertex and all other vertices have their cost as infinity, just because we have not explored it yet. And the next step is we have from A 2 vertices are reachable, which are B and C, and so we update their cost in this table. And now we put up C as being visited just because its cost is least, and so the cost of reaching from C from A is 3. And now let us check what are all the other vertices that could be reached via C. So, you could see that B could be reached and E could also be reached. Earlier B could be reached from A at a cost of 10, now via C it could be reached at a cost of 7, which is 3 plus 4. So, that cost is cheaper, and so we may have to update it here. And also you could see that not only B, E is also reachable through C, and so the cost of reaching E through C is 3 plus 2, which is 5. That are all the updates that we make up to this table by this time, and as such we have just visited 2 vertices in that graph. So, as such, as I said, we have updated the cost of reaching B by 7, and we have added up the cost of reaching E through C as 5, and after reaching E, I mean there is one another edge we have left out. We could also reach vertex D at a cost of 8, right. So, the cost of reaching D through C would be 3 plus 8, which is 11. That is what we have added up in this state of this table. Now, our aim is to pick up the next vertex with the least cost. In our case it is E, and so we mark it as visited, and so E gets added up to this list. And now we check what are all the vertices that are reachable from E. So, there is only one vertex D which is reachable from E. In our case the cost would be 3 plus 2 5, 5 plus 9 it is 14. Whereas, the earlier cost to reaching D through C is even cheaper than that, and so we do not update this table. Our objective is to find the shortest path, and if at times we get up, I mean we reach out a cost which is higher than the already present value, we do not actually update the table. And then we go on for finding the next possible choice for us. So, among the vertices that are all not visited yet, for us the next choice would be to pick up either B or D, of which B is the least, and so we pick up B. So, now we mark B as visited, and now we check what are all the vertices that are all reachable from B. So, from B I could reach D, also I could reach C. So, when it comes to C, C is reachable through B at a cost of 11, whereas already it is visited at a cheaper cost. So, we do not update it, and also D, there is a possibility of visiting D through B, but the cost already present cost is 11, whereas this cost is 12, which is higher. So, we do not make any updates here. Now, the last vertex to be visited is only one is left out, which is D, and so we try to reach out to D. And before that, one thing what we have missed is that while yes, D is the next vertex to be visited, and you could see that as you take the path to D via B, its cost is 12, right. And you could see that if we reach this vertex, I mean D via C, then its cost is 4 plus 3 plus 2. So, as soon as we mark B as visited, we have one more alternate way of reaching out to D through B. So, we feel that this is the least cost, and so its weight is being getting updated, right. And so, now as you see that the graph had only 5 vertices, and we have visited all those vertices, and you could see that all the vertices are reachable, have been reached via following edges with the least cost. So, we find end up with solution as this is the path, this is the shortest path. So, the way to reach this from the start vertex is A, C, E, B, D, and in order to compute the cost, we are supposed to find, I mean sum up all these values that are shown highlighted, that would be the total cost of this path. So, as such this algorithm gives you two things as output, one is the tree which is this, and other one is the minimal cost of this path or the shortest path and its cost. So, there are two ways of implementing this algorithm, Dijkstras algorithm. So, you could use either a list or you could use a priority queue. Whatever be the data structure that you use, the complexity for this particular algorithm would be of the order of V square, because after reaching out to, we will be initializing all the vertices once. So, which is order of V, and we have a loop that runs number of vertices time, where we possibly explore all the edges that start from a particular vertex. So, altogether it would be order of V square plus E, which is order of V square. And we have one more kind of problem called as all pass shortest path. So, here in Dijkstras algorithm, we find the shortest path to any node in that graph from the single source, whereas we have this kind of problem where we will be having shortest path to any pairs of vertices. This same Dijkstras algorithm can be used for this finding the solution for all pairs shortest path, but the algorithm has to be run n number of times. We may have to repeat it n number of times for every, I mean by assuming every vertex as a start vertex. And there is another category of algorithm for shortest path, which relies on dynamic programming. We call that algorithm as Bellman-Ford algorithm, and of course, we are going to study next about Warshall's algorithm, which relies on dynamic programming, which is meant for all pass shortest path, and as such since it also falls under the category of dynamic programming, I have not put up this Bellman-Ford algorithm here. And here I have given you some practice questions where you can apply this Dijkstras algorithm and check whether you are able to find the lowest cost from the start vertex for these two graphs. And as such, to summarize what we have seen so far, we were studying about this shortest path problem, or finding the solution for this shortest path problem, and our objective is to find the minimum distance or minimal cost path from between two vertices in a graph. And this particular algorithm can be applied for all sorts of graph like directed, undirected, weighted and unweighted. But to be specific, when you talk of unweighted graph, it is better to go with the breadth first search, which we learnt before with the graph traversals. and specifically for weighted graphs, and that too the graphs where the edges are all non-negative, Dijkstras algorithm is the best choice. If suppose in a weighted graph the edges have weights which are negative, in that case it is good to go with the Bellman-Ford algorithm. And here out of the, I told you that there are two possible ways of for implementing this Dijkstras algorithm. You could go either with priority queue implementation or a list implementation. And if suppose your graph contains negative weights, then it is better to go with Bellman-Ford algorithm. And probably with the next lecture we will be learning about proposing solution for all pass shortest path problem. And here I have put up some questions to test our understanding of the concepts. So, first question is that why can't Dijkstras algorithm handle negative weight edges? Because as I said, it is a greedy approach. If in case our edges have negative weights, then as we find the total cost of the path cost would get on decreasing, right? And then we will not be able to find the solution, I mean we will not be able to come up with the solution with the least cost. And so we say that Dijkstras algorithm is not suitable for graphs with negative weights. And then when would you prefer Floyd-Warshall algorithm over Dijkstra? As such, this Floyd-Warshall algorithm, it's a algorithm for all pass shortest path. So in that case, as I said, Dijkstras algorithm can be used for that problem, but it has to run n number of times. Rather, it is better that you go with the Floyd-Warshall algorithm, that is specifically for all pass shortest path. The third question is, what does it mean if Dijkstras algorithm returns different paths for the same source target pair with the same weight? So there is a possibility, because in a graph we will be having multiple edges between any pair of vertices, and so we may end up with the same cost for different paths. In that case, it is our choice to choose any one among the available choice of source target pair. And then how is the shortest path in an unweighted graph computed? As I said before, when it comes to unweighted graph, instead of going for this Dijkstras algorithm, it is better that we use the breadth first search which we learnt with graph traversals. That is good to go for finding the shortest path for an unweighted graph. Hope you have understood the concepts of shortest path problem and how we can come up with a solution for single source shortest path problem, possibly with this Dijkstras algorithm. And